Hi everyone, I'm Sam Galotra from University of Massachusetts Amherst. I'm going to present our work titled BL, Blocking for Effective Entity Resolution. This is joint work with Donatella Fermani from Brahmatra University, Barna Saha from UC Berkeley, and Devesh Srivastava from AT&T. To give you a high-level overview, entity resolution, or ER in short, is a task of identifying groups of records that refer to the same entity. It is a challenging problem and has been widely studied for more than 50 years under different names like reduplication, record linkage, and entity linkage. As an example, consider a collection of 9 images of different tourist locations collected from various travel websites. If we perform entity resolution on this dataset, we get 4 clusters, with the blue one referring to the replica of Eiffel Tower in Las Vegas, yellow referring to the Colosseum in Rome, red referring to the Eiffel Tower in Paris, and green corresponding to the Leaning Tower of Pisa. Entity resolution is useful for many applications. For example, Amazon uses ER to cluster different listings that refer to the same product but are sold by different sellers, as I show on the right. Government uses ER to link census records with administrative records. It is also useful for knowledge graph construction, improved web search, and constructing healthcare registries. However, the increased availability of data from a variety of sources has raised the importance of designing scalable techniques to perform ER. In this work, we study this challenge and demonstrate a feedback-based blocking mechanism to perform entity resolution on datasets containing millions of records. Let us look at a traditional ER pipeline first. Traditional ER pipelines consist of two main components. The first component is called blocking. Blocking aims to efficiently prune out pairs of records that refer to different entities and generate a small set of candidate record pairs that are considered for subsequent stages of the pipeline. The second component is pair matching and clustering. This component compares the input candidate pairs and forms clusters referring to different entities. Let us look at an example of a blocking technique. The table on the right shows a textual description of the images we saw earlier. Using these descriptions, we illustrate token-based blocking that generates a block for every token in the dictionary. Here we show two blocks corresponding to the tokens Eiffel and France. A block contains all records that have the corresponding token. For example, the block corresponding to France contains only 3 records. After constructing these blocks, blocking never compares any record pair that does not share a block. For example, records 1 and 5 do not share a block in the entire dataset and would never be considered as candidates for any subsequent steps. There are many other advanced methods that have been proposed to generate, rank, and prune blocks of different sizes. By varying these parameters, we can simulate a varying number of candidates generated by blocking phase. Now, if we restrict our blocking algorithm to generate very few blocks that are of small size, then many matching record pairs would be pruned and would lead to loss of recall. If we allow the blocking algorithm to generate large blocks, then it would achieve high recall, but it would suffer from poor efficiency. Therefore, all these techniques suffer from poor effectiveness efficiency trade off, and blocking techniques are well known to require a lot of manual fine tuning. To deal with these challenges, we had an intuition that why can't we use the output of pair matching and clustering component to fine tune blocking? If we do that, we don't have to consider blocking as a pre-processing step and can possibly use additional knowledge to improve its quality. We tried this mechanism and proposed new architecture where blocking and pairwise comparisons are performed in tandem. At a high level, the pipeline is initialized with a default setting of blocking strategy, and it is used to generate candidate pairs for pairwise matching. Then a small subset of the candidate pairs are compared, and its output is fed back into the blocking to fine-tune it. This updated set of blocks generates new candidates, which are used to perform matching on a new subset, and then again its output is fed back into the blocking. And this goes on and on until the blocking converges. Due to this feedback from the matching phase, We are able to identify which blocks contain more matching record pairs and which ones don't. Similarly, the feedback is also used to construct new blocks that are refined and contain more matching record pairs. Let us go over these components of blocking that are improved with feedback. First, block scoring. Block scoring component aims to rank blocks that contain more matching record pairs higher than the ones that contain fewer matching record pairs. In the absence of any feedback, prior techniques rank blocks based on their size, assuming that larger blocks contain noisier records. This does not hold in modern settings where records are collected from multiple sources and data can have a skewed distribution of cluster size. For example, the image on the right shows the records of Cora dataset with pairs that refer to same entity are connected by a blue colored edge. As you can see, some clusters are quite large, and while there are many small size clusters too. Using feedback from pair matching, we propose to calculate quality-based score for each block. This score contains two components. First component estimates the fraction of matching pair in the block, and the second component calculates the entropy of cluster distribution within the block. These estimates help to rank blocks that have higher fraction of matching pairs and larger clusters higher than the rest. However, accurate estimation of these scores requires information about matches and non-matches in the blocks. And this information is not available for all pairs. To deal with this challenge, we leverage pairwise similarities between record pairs to initialize such scores, and the estimates are refined with feedback from the matching phase. In addition to block scoring, we also propose a block refinement mechanism that creates a multi-level hierarchy of refined blocks. A refined block is generated by performing an intersection of the original set of blocks. In this example, we show a two-level hierarchy where the first level contains singleton tokens that refer to initial set of blocks generated from tokens. The second level corresponds to the conjunction of tokens and contains more refined and smaller sized blocks. I won't go into the details of how these blocks are constructed efficiently. Please refer to the full paper for more details and theoretical guarantees of a proposed mechanism. Let us empirically compare the benefit of performing blocking and matching together in tandem. This plot compares the recall of blocking phase for two data sets for three different blocking settings. Purple bar is the traditional pipeline, and green bar is the BF pipeline that uses feedback. This experiment shows more than twice improvement in recall whenever blocking is employed with feedback. In this experiment, we compare the pipelines under two different settings. The left half of the table compares running time of the pipeline with and without feedback with a constraint that it should achieve more than 0.95 pair recall. The right half compares the S-score of the pipeline, assuming they are run with a time budget of 1 hour. So notice that in this experiment, we vary the parameters of blocking to make sure that this constraint of either recall or time budget is satisfied. In both experiments, BR performs considerably better for large-scale datasets. On small-scale datasets like Cora, products, and cameras, both techniques perform similarly. Let us now visually compare these techniques through the demonstration. At the beginning, a user can input a dataset in CSV format or choose one of the pre-selected options, which includes cars, camera, DBLP, and songs datasets. Let us choose the car dataset for this demonstration. On choosing the dataset, BR shows a snapshot of the data along with a SQL query box. The user can type a SQL query to inspect a smaller subset of the data. For example, let us choose a subset of the data that contains the token Corvette. This subset contains 55 records that match the input query. In addition to the dataset summary, BR also shows the summary of ground truth clusters. To test the ER pipeline with different settings, user can choose blocking and ER algorithm from one of the pre-selected options and choose whether to use feedback or not. If the user wants to further configure the parameters like block graph size, block scoring algorithm, or pairwise matching function, Configure Pipeline tab provides additional functionality. Now, let us run the AR pipeline with feedback and default settings for blocking. The output here shows two different types of plots. The left panel is a hierarchical representation of blocks where size is proportional to the number of records in the block, and color denotes block score, with dark red denoting 0 score and dark blue denoting score of 1. On clicking any of the blocks, the user can further inspect the blocks in a specific subtree. The right panel shows the pairs that have been compared until now. Here, green edges show matching and red edges show non-matching record pairs. The color of each record denotes the entity it refers to. Here, the output is shown for a progress value of 70%. Let us change the progress value to 0% and see the change in output. In this output, block scores are inversely proportional to the size. Therefore, all large blocks have a score close to 0. There is no edge in the right plot because pair matching has not been performed. Now let us turn progress to 100% and see the change in output. When we do that, the left panel shows converged scores of blocks where many large blocks have a high score. For example, Chevrolet C6 has a high score even though it's a large block because it contains majority of matching record pairs. This block had a low score initially because of TF-IDF based scoring to initialize the pipeline. The right panel shows all pairs that have been compared. Now, the output panel summarizes the overall performance of the pipeline and compares progressiveness with respect to the ideal curve. Moving on to the last tab, Beer allows the user to compare different blocking techniques configured with different parameter values. The user can select two different settings of the pipeline and compare their quality. Let us see how feedback helps token-based blocking in Cars dataset. The output compares the quality and running time of two input settings along with three visuals. The table shows the feedback-based pipeline has better quality but has slightly higher running time. The second visual compares a difference in scores of different blocks. The third visual shows a set of pairs compared by the two techniques. This shows that Technique 2 compares many more pairs than Technique 1, and majority of the pairs compared by the first technique are matching as compared to that of the second technique. The plot on the left compares the progressive change in quality of pipelines with the number of pairs compared on x-axis and F-score on y-axis. In this way, Beer demonstrates an interactive visualization to compare different blocking techniques with and without feedback to understand the effect of different inputs and parameter settings. Thank you for listening. Please feel free to contact us if you have any questions.